All right, friends, last time we were talking about the Diels-Alder reaction, in which we react a diene with a dienophile or an olefin to make a new cyclohexene ring. Recall that we were talking about Diastereo Specificity related to the olefin and the cyclohexene product, which is that if two substituents on the olefin are cis to each other before the reaction, they must also be cis to each other in the product. Now remember, we're envisioning this Diels-Alder reaction happening by looking at the diene on its side, orange carbons 1 and 4, making new bonds with purple carbons 1 and 2. And notice that I've chosen, at least in this case, to have the two ester substituents on the olefin pointing upward. In red dotted line, that's the new bond I'm making, new sigma bonds I'm making, and as you can see, relative to the new ring that we're forming, these ester groups are above the ring. They must be on the same side of the ring. There's not enough time during the concerted reaction for there to be rotation around this bond between 1 and 2 as it goes from a double bond to a single bond. Some of you may have asked, well, what if I instead chose to have the olefin approaching the diene with the substituents on the olefin pointing downward? And the answer to that is, in this case, you would have gotten the same meso product. These two are identical. Of course, if we started instead with the trans olefin and reacted this with our diene, we would, in a Diels-Alder reaction, again would have made the 6-membered ring. Only this time, substituents that were on the dienophile or the olefin that are trans have to be trans in the product. And of course, if I make stereocenters and if my product is chiral, but my starting materials were not chiral, then I have to get both enantiomers, which is what I have indicated with this plus minus. However, notice that the stereochemistry of the olefin, cis versus trans, influences which diastereomer we get in terms of the product. If we use the cis diastereomer of the olefin, we get the cis diastereomer of the cyclohexene product. If we use the trans diastereomer of the olefin, we get the trans diastereomer of the cyclohexene product. Now let's consider diastereo specificity as related to the diene. But before we do this, we need to talk about something that I didn't tell you in our previous discussions of the Diels-Alder reaction. And that is that the 1,3 diene, as we've drawn it here, can exist in an equilibrium between these two conformations. This is the S trans conformation. This is the S cis conformation. The S cis conformation is less stable than the S trans conformation because of steric repulsion between these two hydrogens that are pointing sort of to the inside of the S cis conformation of the diene. The S trans conformation is more stable because it doesn't have that steric clash. However, the diene must be in the S cis conformation to participate in the Diels-Alder reaction, because that's the conformation that gets orange carbons 1 and 4 on the same side of the molecule. And as you can see, if we draw a diene in Spartan and then look at the space-filling model, you can see that it's not completely flat, and that's because the two hydrogens on the terminal CH2 groups would bump into each other if this were perfectly flat. And so that's one of the reasons why we have to add heat to the Diels-Alder reaction to get it to go, because we need to access this less stable, higher energy conformation. All right, so that's important. That the idea of the S-cis conformation is important because on a diene, because that diene has to be in that conformation, there's going to be a distinction between groups that are pointing outward or outside of the diene and its S-cis conformation versus groups that are pointing inside. And we need to keep that distinction in mind as we think about how the stereochemistry of the diene influences the product of the Diels-Alder reaction. So here's the original Diels-Alder reaction from 1928, which you saw last time. Notice that for this diene, cyclopentadiene, it is permanently constrained as in the S-cis conformation, because in cyclopentadiene, there's only one inside substituent and it's connected to both orange carbons 1 and 4, so there's no steric problem anymore. And it's permanently constrained in the reactive conformation. However, there are still outward pointing substituents on the diene, and then again this inward pointing substituent, which is actually a substituent of both carbons 1 and 4. So we're now going to draw what we expect to happen as an olefin approaches this diene. So we're going to draw a cyclopentadiene on its side. The only difference between what we've done here and what we've done before is that there's this CH2 group here in the middle that's connected to both orange carbon 1 and orange carbon 4. That blue group is the inside substituent, and the pink groups are the outside substituents. Now, we're going to have an olefin, and I'm going to simplify our olefin for this case, but our olefin's approaching the diene from the side. Here's purple carbons 1 and 2. These are the bonds that we're going to make. In the course of this reaction, we will also break that pi bond, break this pi bond, break this pi bond, and make a new pi bond there. So here is the 6-membered ring that we're going to form in this reaction, and notice that relative to that ring, the inside substituent, that blue group, the CH2 group, is going to be above the ring, whereas the outside substituents, the pink hydrogens, are going to be below the ring. So we can draw the product of this reaction. We do so simply by drawing a 6-membered ring, cyclohexene. These are the atoms that belonged to the diene and the olefin respectively. Carbon 1 and 4 are here. Carbons, purple 1 and purple 2 are there. The inside substituent is hovering above the ring and is connected to both carbons 1 and 4, whereas the outside substituents, those 2 pink hydrogens, should be angled downward. Okay? So the key element of Diastereo specificity as it relates to the olefin is that the outside substituents in the diene must be cis to each other in the product. And the same thing would be true if we had more than one inside substituent. All right, let me give you an example of this that doesn't involve a cyclic diene. All right, so let's use this 1,3 diene in which there are methyl groups pointing outward and hydrogens pointing inward. Again, we will label the outward substituents in pink and the inward substituents in blue. And we're going to react this with the same olefin as we've done previously. Now let's draw the diene from the sort of side-on perspective. On carbon 1, we have a methyl group on the outward position and a proton on the inward position. So here's the proton, and then sort of angled outward. Oops, dang it, losing stuff. Sort of angled outward is the methyl group on orange carbon 1. We'll label that methyl group in pink. The proton is an inside group. We'll label it in blue. We've got another one here, also labeled in blue, and then another methyl group here. Okay. And again, we will bring our familiar dienophile or olefin to approach the diene. We're going to use dotted lines to represent the new bonds that we make between orange 1 and purple 1, and between orange 4 and purple 4. Also, we're going to break these pi bonds and replace with a pi bond there. Cyclohexene product will then be, here's my 6-membered ring with the double bond. Here's carbons 1, 2, 3, and 4 orange from the diene, and carbons 1 and 2 purple from the dienophile or the olefin. Now let's fill in the substituents on carbons 1 and 4. The hydrogens, the blue hydrogens, must, in the way we've drawn it here, are hovering above the ring, and they are cis to each other. Whereas the pink methyl groups are also cis to each other, but are pointing downward instead of upward. So the methyl groups are cis to each other, but trans to the hydrogens. Notice the groups that were pointed outward are cis to each other, and the groups that were pointed inward are cis to each other, but inward groups are trans to outward groups. Now some of you may wonder, how do I know that things work out such that the hydrogens are above the ring? You don't necessarily need to draw it that way. You could have drawn it like this, and that's a perfectly acceptable product. And in fact, you'll be able to see if you just pancake flip this molecule over from this perspective, turn it over towards the top of the page, you have exactly the same thing. All right. Let's illustrate that. Again, the point that the inside stuff stays cis to each other and the outside stuff stays cis to each other by changing the stereochemistry of the diene. Let's, instead of this E stereoisomer, let's try this EZ stereoisomer, in which on orange carbon 1, the methyl group is outward, whereas the proton is inward, but on orange carbon 2, or sorry, getting a little confused, orange carbon 4, the methyl group is pointing inward, whereas the proton is pointing outward. All right, and let's use the same simple olefin that we've been using. Again, we'll draw the diene as though we're looking on it from the side. Notice that orange carbon 1 has the proton pointing inward, whereas orange carbon 4 instead has the methyl group pointing inward, 1 and 4. Then notice that on orange carbon 1, the methyl group is at an outward position, whereas on orange carbon 3, it's the proton that occupies the outward position. All right, so now, as we've done before, we will have our olefin approach the diene. We're going to choose this side arbitrarily. We could have it approach from the left side as well. These are carbons 1 and 2 of the diene. We're going to make a bond between orange 1 and purple 1, between orange 4 and purple 2. Notice that as we make the new 6-membered ring, the proton on on orange carbon 1 will be above the ring, as will the methyl group on orange carbon 4. Okay, so proton on carbon 1 we said was above the ring. Methyl group on carbon 4 was above the ring. Notice that the two groups that were inward in the diene are now on the same side of the ring as each other, whereas the two groups that were outward on the diene are also cis to each other, but on the other side of the ring. The pink stuff is cis to each other, the blue stuff is cis to each other, but the pink and blue are trans. Okay, and in this case you would notice that our product was chiral, and so where would we get the other enantiomer? We would simply get that if we had said that proton on orange carbon 1 was down, whereas methyl group was up. And then a proton on orange carbon 4 was up, whereas methyl group was down. And that just happens to be the other enantiomer. And you would get that possibly by having the olefin approach the diene from the other side. But in any case, as long as you remember that if you make a product that's chiral, but your starting materials were not, you must make both enantiomers. Okay, so that's Diastereo Specificity second issue, the diene. So we've talked about Diastereo Specificity relative to the olefin and the diene. And the principle is stereochemistry of the olefin influences which diastereomer you get of the product. Also stereochemistry of the diene, EE versus EZ. This diastereomer gives you a different product diastereomer versus the EZ diastereomer, which gives you these two enantiomers. All right. Now, up until now, we have kept our examples deliberately simple. So far, I have not shown you in detail a reaction in which both the olefin and the diene had substituents. But it turns out that that is exactly the case for the original Diels-Alder reaction. So we're going to talk about issue number 3, which is Diastereo Selectivity. And this is the relationship between substituents on the diene with substituents on the olefin. All right, so I'm going to copy our original Diels-Alder reaction. And I want you to notice, here's carbons 1 through 4 of our diene, 1 and 2 of our olefin. I want you to notice that we're keeping the rules that we've learned previously, The substituents that are outward on the diene are also cis to each other on the 6-member ring product that we make. And people get confused a little as to which carbons over here are from here. Remember that the 2 bonds we make are here, so carbons 1 and 2 come from the olefin. That means these CH bonds for these hydrogens must also come from the olefin. So presumably we get this product from approach of the diene and the olefin and the olefin is going to have protons up and other substituents down. I'm going to call carbon 6 and 3 and the stuff that they're attached to just this R group. Okay, so if we have the olefin and the diene approach in this way, we would get the product shown above. Not drawn was the product in which the olefin and the diene approach each other with the protons on the olefin pointing downward instead of upward. So in other words, what if we flip the olefin so the R groups were going this way? If we had done that, we would have expected to see the following product in addition to the one that was drawn to the left, and that is protons are down, R groups are up. All right, so the relationship between these 2 products is diastereomers. You can tell that because we've switched stereochemical configuration at these 2 stereocenters, but not at the other ones in the molecule. And we have a special way of talking about these 2 diastereomers. So notice the groups I'm highlighting. In pink are the outward groups on the diene. In blue, that's the inward group or groups on the diene. And then in a darker red, I'm going to highlight the R groups on the olefin. And then just to demonstrate, I'm going to redraw the products down here. And I want you to pay attention to the stereochemical relationship between the blue group, the one that used to be inward on the diene, and then the red groups, the ones which are cis on the olefin. And in this case, those R groups are down. So this would be what our product looks like. And so we're going to pay attention to the relationship between the blue group here and the red groups here. If blue and red are on opposite sides, sorry, getting a little bit behind. If blue and red are opposite or are trans to each other, we call that the exo. I'm getting it wrong, sorry folks. If blue and red are opposite to each other, we call that the Endo Diastereomer. In contrast, if blue and red are on the same side or cis to each other, then we call that the Exo Diastereomer. again, always focus in on the relationship between the blue group, that is the group that was inward on the diene, and then the red groups, that is the groups that were cis to each other on the olefin. So this is the Endo Diastereomer, this is the Exo Diastereomer. A rule of thumb that applies sometimes, it's just empirical, it's just been observed, is that the endo product is usually preferred. Now, I'm not going to ask you to tell me which is the preferred product, though I will ask you, when possible, to identify which is endo versus exo. Okay. So the distinction between endo and exo diastereomers sometimes isn't possible. And one case in which it's not possible is when there are when you have two different groups on the olefin that are trans to each other. This ends up getting pretty confusing. You can draw two different products. They end up being enantiomers of each other. And again, we can compare the relationship between the two groups, the group or groups that was inward on the diene, and then the groups on the dienophile or the olefin. The problem is that one of the groups on the olefin is cis to the blue group, and the other is trans to the blue group. And so it's completely unclear whether one is endo versus exo. You'd have to specify which of these two you were talking about, and that just gets confusing. And in that situation, we don't bother assigning endo versus exo at all. All right. Let me show you one more example where assigning endo and exo is possible. And we will do this in the context of a diene that is not cyclic. And again, we're going to pay attention to the groups that are pointing inward on the diene. And then let's use this olefin. All right. So again, groups that are inward, groups that are outward on the diene, and then groups that are cis to each other on the olefin. So here's my 6-membered ring. Here are the 4 carbons from my diene. Here are the 2 carbons from my olefin. The inward substituents will start by putting them upward, and the outward substituents will put those downward. And then we can show either the red groups on the olefin, on the cis olefin, being on the same side as the inward stuff from the diene. And if it were on the same side, we would call that exo, or alternatively, we can draw the red substituents on the olefin going in the opposite direction, downward. And this would be the Endo Diastereomer. Okay, and it all has to do with the relationship between the groups that were inward on the diene and the groups that are cis to each other on the disubstituted olefin. Now, again, you can think of lots of things you could do to this olefin to make it so you couldn't assign endo versus exo, and that's fine. When you can assign it is when the olefin has two groups that are cis to each other. All right, so that's the diastereo selectivity piece. The last thing we need to consider is regioselectivity. And this is interesting because if you go back and look at all the examples that we've done, including this one that's immediately in front of us, carbons 1 and 4 on the diene are identical, and carbons 1 and 2 on the olefin are identical in our starting materials. And this has been true all the way through. Where at least one of them is identical by symmetry. It was certainly true in the original Diels-Alder reaction. You could argue here that in this example, carbons 1 and 4 were not identical. One is in an E double bond, the other's in a Z double bond. However, the olefin, the carbons of the olefin were identical. And because of that, we have never had to worry in these examples, we've never had to worry about whether orange 1 makes a bond with purple 1 or with purple 2. And similarly, whether orange 4 makes a bond with purple 2 or with purple 1. That issue of which sigma bonds we make between orange 1 and 4 and between purple 1 and 2 is the issue of regioselectivity. That is, do we make the following bonds, orange 4 and purple 2, orange 1 and purple 1, or orange 1 with purple 2 and orange 4 with purple 1. So we're now going to introduce what you do when that becomes an issue. And understand that we're only going to deal with situations where you could reasonably predict which of the two options was better, whether it were orange 1 with purple 1 or and orange 4 with purple 2 or the other option. So let me give you an example of a case where we can make that distinction. So here is a diene, and it's got an amino group substituent on it. And then here is an olefin, and it's got a couple of different substituents on it. It's got an ester group on carbon 1, we'll say, and a methyl group on carbon 2. And so we have to consider among our possible options, but I'm not going to worry about stereochemistry here. I'm going to draw the possible regioisomeric outcomes. One would be where I form the 6-membered ring by making a bond between orange 1 and purple 1, and between orange 4 and purple 2. And again, without worrying about stereochemistry, this is the sort of regiochemical situation I would have. Okay. In contrast, if I did the other connectivity, that is, if I had orange 1 bonded to purple 2 and orange 4 bonded to purple 1, I would have the following regioisomeric outcome. Do you see how these two options, these two different connectivities, related to the two sigma bonds that we make? Do you see how those lead to different products? Do you see how their connectivity is different? Isomers that differ in connectivity are called regioisomers. So we have these two regioisomeric possibilities. Now, which regioisomeric outcome is best? Can you even tell? Sometimes you might not be able to tell, but a classic example of a time where you might be able to tell is when we have an electron donating group on the diene and an electron withdrawing group on the olefin. And it just so happens that the amino group is an electron donating group. What do I mean by that? I mean that we can draw a resonance structure. We can draw a few different resonance structures in which we put we take the lone pair that was on the nitrogen and we move it to form a pi bond between nitrogen and carbon. Then if we stop there, we'd have too many bonds to carbon. And so we move this pi bond over, and then if we stop there, we'd have too many bonds to carbon, so we move this pi bond over as a lone pair on carbon 4. So that tells us something. It tells us that carbon 4, which I'm going to highlight in gray, orange carbon 4 is electron rich. Now, some of you might be saying, couldn't you draw a resonance structure where there was a negative charge on carbon 2, and wouldn't carbon 2 be electron rich as well? Yes, of course, but carbon 2, orange 2, is not involved in bond making in the Diels-Alder reaction, or at least not involved in making the sigma bonds. So, and since the regioisomeric issue has to do with which sigma bonds we form, I'm trying to identify whether carbon 1 or 4 is electron rich. So we conclude based on resonance that orange 4 is electron rich. Through similar arguments, we can determine that we can look and see whether one of the two carbons of the olefin, 2 versus 3, getting stuff wrong here, sorry, 1 versus 2, whether one is more electron poor than the other. Whenever you have a carbonyl adjacent to a pi bond, this is a situation in which you can draw a resonance structure that would put a lone pair with a negative charge on the oxygen and a positive charge on the carbonyl carbon. Then whenever you have a pi bond adjacent to a positive charge, that is a situation in which you can do resonance where the pi bond moves over to make a new pi bond and the positive charge goes on to carbon 2. Okay, so we would therefore conclude, I'm going to highlight it in gray again, that carbon 2, purple carbon 2, is electron poor. Now, do you see how this maybe makes one of these regioisomeric outcomes better than the other? The best regioisomeric outcome comes from approach of the olefin towards the diene such that the electron-rich carbon on the diene, carbon 1 or 4, in this case 4, lines up with the electron-poor carbon on the olefin, in this case purple carbon 2. So that means that we're preferentially going to form a bond between 1 and 1 and between 4 and 2. Because the other approach would not have the electron-rich portion of the diene line up with the electron-poor portion of the olefin. So with that in mind, let's draw the outcome, and in this case, and this time, let's deal with stereochemistry. Here is our 6-membered ring. The diene only has one substituent, and it is the outward nitrogen group. The olefin has 2 substituents, and they have to be trans with each other. And remember, I'm going to make sure as I do this that orange 1 is bonded to purple 1 and orange 4 is bonded to purple 2. Purple 1 has an ester group on it. I'm going to choose for this diastereomer to have that ester group pointing upward. Because that ester group was trans to the methyl group in the olefin, it must also be trans to the methyl group in the product. This product is chiral, and my starting materials are not, so I have to have made both enantiomers, and I can get that other enantiomer if the olefin approaches the diene from the other side. And then I have to deal with the other diastereomer. That is the one where the amino group continues to be pointing downward, but now the ester group is down and the methyl group is up. And these two, of course, we would form the other enantiomer of this molecule. These two are diastereomers of each other. Now, can we say which is endo versus exo? And the answer is no, because though we could identify a group that is pointing inward on the diene, we can't say whether that group is on the same side or on opposite side to the substituents on the olefin, because the substituents on the olefin are not cis. So no endo-exo assignment is necessary. All right, and finally, we don't, of course, it doesn't have to be that the diene is electron rich and the olefin's electron poor. You can draw a diene that has, say, an ester group here and an olefin that has a methoxy group here. And again, we're going to consider the impact of electron donating versus withdrawing groups. For the diene, I notice that I have an electron withdrawing group in the form of this ester, which is adjacent to the carbonyl carbons adjacent to the pi bond, which means I can draw a resonance structure in which I move the electrons out onto that oxygen to create the following resonance structure, which would have a plus charge on what we're going to call orange carbon 1. I can also draw a resonance structure in which I have lone pair electrons on the olefin donate in to place a pi bond between carbon 1 and oxygen with a positive charge on oxygen, and then a lone pair and a negative charge on carbon 2. So that would tend to tell me that the electron poor portion of the diene was here on carbon 1, whereas the electron rich portion of the olefin is here on purple carbon 2. So, which regioisomeric outcome am I going to want to get from the Diels-Alder reaction of these two molecules? Is it going to be the one where I have 1 and 1 connected and 4 and 2 connected, or 1 and 2 and 4 and 1? Remember, I want to line up the electron-rich portion of one molecule with the electron-poor portion of the other molecule, which would tell me that perhaps the best way of approach would be for the olefin to approach the diene such that electron-poor carbon 1 of the olefin can line up with and be near electron-rich carbon 2. I'm sorry, orange 1 of the diene, electron-poor orange 1 of the diene, can be line up with and be close to electron-rich purple 2 of the olefin, and then the regioisomeric outcome is this one. We're going to have the ester group here, the methoxy group there. That's chiral, will also have its enantiomer. Then we could also draw the other diastereomer in which the methoxy group and the ester group are on the same side. Technically, you could assign endo versus exo here because it's clear based on the identity of this proton and then the substituent, the one substituent on the olefin. We could technically call this enantiomer the exo, this diastereomer the exo diastereomer, and this one the endo diastereomer. But doing so would probably be pointless because of the few substituents we have on each group. I would simply want you to draw me both of them, but to draw the correct regioisomeric outcome. All right, one last thing. I told you that endo was generally preferred, and there's some potential explanations for this, though they're controversial. One is that the R substituents on the olefin tend to have pi bonds in many cases, and it's possible for the pi orbitals associated with these R groups on the olefin in the endo transition state, if they're near the carbons 2 and 3 of the diene, some people have proposed something called secondary orbital overlap, where you have these orbitals on the R groups and then the pi orbitals of the diene, especially carbons 2 and 3, that are not close to each other in bonding, but are sort of close in space in the endo transition state, but not in the exo transition state, which I'm sort of showing you here with these red dotted lines. However, there's an alternative explanation, and that is that the shape of the endo transition state, if you think about the atoms that are involved in making bonds, it sort of looks like this from the side, whereas the transition state for the exo diastereomer sort of looks like this. And the idea is that the endo transition state is more compact, whereas the exo transition state is more extended. And so the argument is that the endo transition state is lower in energy because it requires less rearrangement of solvent molecules nearby. In this extended conformation, you'd have to rearrange the solvent molecules more because the extended conformation isn't as compact. That's not important for this class. You don't need to memorize it. I just wanted you to have an idea of the origin of the empirical observation that endo is usually preferred, and a sense for the fact that it's still, the precise origins are somewhat controversial. Okay, so that concludes our discussion on the Diels-Alder reaction. When we start up again, we will talk about radical chemistry.